Hi friends, let's now try to understand all these concepts putting on the timeline. So that's a timeline, and there are some algorithms which can be solved in polynomial time. So we can call this the P class of algorithms. Then there are algorithms which can be solved in exponential time. So we can call them exponential class algorithms. Yes, there is a special place on the timeline where the problems lie and they cannot be solved in polynomial time. They can be solved in exponential time, but they can be verified in polynomial time. So we can call them a NP class of problems. So as we move ahead, then we can think of that's a P, that's a NP, that's a exponential. So that's the boundaries. So we come across another boundary which says that all these problems are solved in real time. That means there are problems for which there is a solution, and there happen to be some problems which have no solution. So as you move away from this on the line, so the problem gets harder and harder. Okay, that's something we can talk of. A polynomial type of problem is a one. So if we just look at the various definitions, so P class, so we can make it a better. So we can say the class. So how much time required to solve and how much time required to verify. So talking about P time, all the problems which are in P type can be solved in polynomial time, and definitely they can be verified in polynomial time. That is, the solutions of these problems can be verified in polynomial time. So we can say that all the problems which are in P class are also in NP class, because NP class is a one which says that the results can be verified in polynomial time. Yes, so the P type of problems can be solved in polynomial time and can be verified in polynomial time. And there is another class, NP class, where this may take exponential time to solve, but once the solution is made available, it can be verified in polynomial time. Then we have an exponential time. So this is one which needs exponential time to solve, and also needs exponential time to verify. and so on. So the examples for polynomial time can be addition, subtraction, multiplication, then searching, sorting, and so many other things. Now coming to NP, yes, we have 0-1 knapsack problem, then we have traveling salesperson problem, then we have Sudoku, then we have Minesweep, and so on. Yes, the problem 0-1 knapsack problem is basically an optimization problem, but we have converted this 0-1 knapsack problem and traveling salesperson problem into a decision problem, stating that the solution given, can it satisfy this 0-1 knapsack problem such that the minimum or the maximum weight can be so and so, or can we decide that the given path, will it be efficient so that the path length is less than or equal to something, instead of asking the best path. So we can say, so can we travel through this path and make up within this distance? Yeah, Sudoku, of course, it is a very complicated problem when it comes to Sudoku. So usually we work on 9 by 9, but if you increase size of this, it goes to terrific, and it just impossible to solve this. But if the solution is available, definitely in real time we can verify whether the solution is correct or wrong. The same happens with the Minesweep and all that. Now exponential. So in this, chess comes in exponential. Why? Because to solve the problem we need an exponential time, but after making a move, if somebody asks, is it a best move? Yes, we can't answer this question in polynomial time. Therefore, we can't put that under NP. It still is outside the NP. So we can say that chess happens to be here, and some thing like reset problem can be here. All other problems are shown here. So that's problems where you can solve in polynomial time. So this some way we can discuss upon and try to understand what we are trying to look at. So the main concern is try to reduce the complexity of the problem to a simpler one so that it can be made manageable while solving it.